Good morning, everyone. So I'm Niki Vazou, and I'm going to do a review of types 1 session. So typing, since I developed the derivation tree to prove some program properties. For example, here I want to prove that 40 plus 2 has type integer or is well typed. And to do that, we can go and construct the derivation tree. And I thought I would not get into much details because I assume that most people here know how this is done, know these rules. Okay, so in the types 1 session, there is one paper that is actually using this structure that the type derivation provides to do actually synthesis, so it will go to the other session too. And then there are two papers that extend the expressiveness of types, one with index types and one with JDTs. And then there is the last paper of the session. It's using the type derivation as a proof system to talk about what happens to actually ill-typed programs. So this is the first paper, generating well-typed terms that are not useless. And the problem is, like, since we have the type derivation, how can we synthesize functions? And they take it further, and they have a goal that the functions actually use their arguments. So the goal is to synthesize an expression of type T. They use this whole T that is common in the synthesis world. And they say to do that, I am going to use type-driven inductive rules. So here I have the standard rule of application for types. And they map it one-to-one to a rule for synthesis. And they say to synthesize an expression that has type T, I'm going to synthesize an expression that has type Tx to T, call it E, and then I'm going to synthesize an expression that has type Tx, and call it Ex, and I'm going to apply Ex to E. Now, this is the idea, but they know that this is problematic because, as they say, Tx is arbitrary, and by arbitrary it means that it doesn't appear in the conclusion of the rules, right? And this is important for this setting. Because if the Tx, if synthesis chooses a wrong Tx, then synthesis can say I cannot go through, so we need to backtrack. But also it's important because the Tx must be chosen before any generation happens, right? And the idea to address this problem is that they say I don't really want to choose a Tx, I can just use some naming to say that this is a variable, this is an argument, and I name them. And on demand, as the synthesis goes on, I can decide if I want to generate this or not. So they use something like this. They say that every time this rule appears, I'm going to create a new identifier. They call it A, and then they use this triangle A syntax to say maybe I'm going to need an argument here. I'm not sure. Like on demand, lazily we will figure it out. And if I don't need it, it's better because I removed one of my arguments. So the contributions of this paper is that they develop a core calculus for term generation. They prove it sound. The proof is mechanized in code. They provide an OCaml implementation. And in the evaluation, they saw that using these techniques of lazy, like on-demand synthesis, the synthesis is faster. And actually, the programs that they synthesize, they are smaller because they have less unused terms. So, in the next paper, they develop index type for statically safe WebAssembly, and the goal is, like, in short, to add index types to WebAssembly. And here I'm going to give a motivation. My syntax is like really simplified, but the idea is that WebAssembly is safe because it does many runtime checks. And as a motivation example, they have division, and they say that at runtime, the semantics of WebAssembly say that to make a division, you have to check, like at runtime, that the second argument is actually bigger than 0. And these kind of checks can be easily statically checked by the type system. So they give, for example, the advisor a type that says, check that your second argument is different than 0. And this is actually very nice. It has many benefits. The first one, that if your program statically type checks with index types, you can remove the runtime checks. All these preconditions that are generated can be easily and automatically checked by an SFT solver. and then the language runtimes are not actually changed. Okay, so these are the contributions of the paper. They develop a core calculus for in-text WebAssembly. They have a soundness proof, and what is cool is they have this embedding proof that basically says if you start from WebAssembly, you add the indexes and then you remove them, you're back in WebAssembly, so the semantics will not change. And this is important when you're dealing with existing languages. They have an implementation as a compiler extension, and in the evaluation they actually show that they were able to remove runtime check, so there is actually a speeder. Okay, and then the other two papers go more on the theoretical side. The first one talks about the sense of generalized algebraic data types, and the problem is they want to prove soundness of GADTs. So here is an example of algebraic data type. So I have a data tree that is recursively defined to be either a leaf or a node. I have my left tree, a value, and the right tree. And if I write this type on the lambda calculus, I'm going to use a recursive type variable beta, and wherever I see a tree A, I'm putting beta instead, right? So we can extend this definition syntax to what we call generalized algebraic data types. And here is an example that the tree is modified to define a perfectly balanced tree. So a P tree is a leaf or a node of a value, and what makes this definition a GADT, it cannot be defined in ADTs, is that here in my recursive call, I am not using A, I'm not using what I have here, but I can put a shape on the arguments. So here it uses a pair arrays. So if I want to write this in calculus, I am using my recursive variable beta, but now beta is not a type as it was before. Instead, it is a type constructor. So it is going to construct a type based on what arguments it gets, right? So this is an example of GADTs. And so GADTs are used right now in many languages. Haskell compiler JC has them, and it needs them to define structures like index vectors, for example. But their meta theory is not was not well established yet. So the questions addressed in this paper is are GADT sounds, or can they be expressed in node systems? In this paper they developed a core calculus for GADTs. The core calculus has an equality sign which implies that something goes wrong with the equality. No, it goes wrong, it's interesting, they solve it. So they have a soundness proof of the core calculus, and they provide two semantic models for it. They actually prove that the GADT core calculus is not expressible in F omega, and they have a discussion that I was persuaded that it's also not expressible in the Cox style type here. Okay, and then the last paper states that ill-type programs do not evaluate, and the goal is to reason about ill-type programs. So this is a standard type system. It has, on the left-hand side, it binds variables to types, and then concludes that some expression has a type. Okay? So the first step is, in this paper they say, I don't want to bind only variables, I'm going to bind arbitrary expressions, so that I have richer assumptions. So by binding arbitrary expressions, I can talk about length of lists or true, false, arbitrary predictors. So in the next step, they say the right-hand side is going to get extended to have multiple derivations. So here I can prove that E1 has type, E1 prime has type T1 prime, En prime has type Tn prime. And the interesting thing is that on the left I have ends, on the right I have or. I prove one of these. And since I have or, it means that empty environment on the right-hand side means that I proved false. So, having this and having also an OK types, that means that types every value, we can use this setting to express that if E is a type, meaning if E has a type, then I say false, then E does not evaluate. And using the same system, I can also prove that if E is well-typed, meaning the standard E has type OK on the right-hand side, then E does not go wrong. So the contributions, they developed this two-sided system, and they use the same system to prove that well-typed programs do not go wrong, ill-typed programs do not evaluate, and they prove the soundness of the system, and also they extended it with branching data types to have an expressive system. And this is the session. Thank you very much, and I hope you enjoy it.